Okay, so last week we talked about this first approach. Okay, and the first approach, the complexity is n cubed log n. Okay, so it is actually worse than um, because the total is higher than n cubed. So where n is the number of nodes, okay, number of nodes in the network. So we obviously, want to see like if there's any other method that we can use to reduce the time complexity. So therefore, we have the following two methods. Okay. So the first one is the Floyd-Warshall algorithm. So supposedly, like you guys, I mean, according to our previous discussion, I mean, you guys have seen this like in your data structure class, okay? But this is what should I say? Like there are like several interesting graph algorithms. Or the Floyd-Warshall is one of them, and the most important thing is that it is a dynamic programming approach. So even though you guys may have, seen this in data structure class, so it will be still a good idea to talk about it more carefully and with more dedicated more time. Okay. So the first approach that we talked about last week, okay, we basically, okay, it's like this. Okay, we basically consider, the path from node I to node J that, go through, for example, in this case, n edges. Okay, so that the previous n minus 1 edges are here, and the last half, is indicated here. So obviously, you have many choices, and the one that has the lowest path weight will be the best, the minimum path. Okay, the shortest path. But the difference between Floyd-Warshall and this one, is that, okay, again, we have seen this, figure. This figure is kind of similar to the previous figure, in the sense that, we are still trying to use to model the whole path. Okay, but instead of just talking about like the number of hops. Okay, now first we do one important modification. The first modification is that we try to change the notation of each node. Say the previous nodes, okay, it may be called A, B, C, D, blah, blah, blah. okay, we are using node 1, node 2, and so on. We call it nodes. Okay, call these nodes. So we have n nodes. So nodes, these nodes will be numbered, okay, from 1 to n. Okay? Well, you just changed the name, right? It doesn't make, the problem any different, right? And this name changing will take linear time to the number of nodes, obviously. So, then, now, after we change the name of the nodes, okay, into numbers, we could, this is how we consider this path. Okay, so we have a node I, node J. Okay? So, we remember, because we have already changed the name of the nodes. So I, J are also numbers, right? It's I and J, they are also numbers. So, instead of consider number of hops, the number of edges used between node I and J, okay, we now, okay, consider what nodes can appear as the intermediate nodes in the path. Sorry. So because like from node I to node J, obviously, in many occasions, you may have like nodes, intermediate nodes, okay, to go through, right? So now we confine this being the intermediate nodes, okay? We say their index has to be, remember like now we use a number for the names, right? So we say the names of the nodes used as the intermediate nodes, okay, their numbers must be, smaller or equal to k, smaller or equal to k. So hence we have this figure from I to J, and all these intermediate nodes. The constraint is that, okay, these intermediate nodes, remember each node now have its number. Okay, each node is a number here. So the intermediate nodes here, okay, their numbers have to be smaller or equal to k. So, under this constraint, from I to J, okay, the best path under this constraint, we call that let me just use the path. P to indicate this path. So path from I to J with the K as a superscript. Okay, so this indicates the path. Okay, the shortest path from I to J that make use of the intermediate nodes with constraint. These intermediate nodes, their numbers are smaller or equal to k. Okay, among all these possible paths, the shortest one. We call it Pijk. Okay, so obviously, okay, such a path may not exist, right? If such a, so first we define the cost, the range for this path, we call it Cijk. We call it we call it C, okay, because C stands for the cost. Okay. So if such a path does not exist, okay, then Cijk would be infinite. Cijk would be infinite. So first, you need to understand the definition of Cijk. And then, okay, when will this constraint be released completely? It will be when k is greater or equal to n, right? Because now, all the nodes in this graph, okay, are numbered from 1 to n. So if you are able to use every single node as the intermediate node, then obviously that means you don't have any constraint for intermediate nodes, right? So the shortest path from I to j, from node I to node j, without any constraint would be, the weight for such a shortest path would be Cij with superscript n. Okay, Cij n. And also, we need to also consider the boundary condition. Cij, okay, from node I to node j, okay, I mean the superscript have to start from somewhere, right? So let's consider the superscript when superscript is 0. Okay, if the superscript is 0, what does that mean? It means, remember, I mean the superscript means like it is the constraint for intermediate nodes, such that all the intermediate nodes, their number have to be smaller or equal to n, right? Smaller or equal to this one. Okay, so when you put 0 as like a superscript, that means like all these intermediate nodes, well, their names, their number have to be smaller or equal to 0. But remember, when we say we rename these nodes, okay, these nodes, the numbers start from 1, right? So there's no node with a number 0, okay? So in other words, when you have the Cij 0, that means you do not allow to have any intermediate nodes in between I to j. So if you do not have any intermediate node between node I to node j, then there are only two possible cases. The first case is that, if there's a direct edge from node I to node j, then obviously you don't need any intermediate node. Okay? So that will be, the weight of that edge. Okay? And if there's no direct edge from node I to node j, then, well, it is impossible, okay, to reach j from I without using any intermediate node. So the weight will be infinite. Okay, so that happens to be the same as the Aij, the adjacency matrix, Aij, the value of Aij. Okay, so this is nice. So we have boundary condition. We have like what we want to compute, okay, as a goal. The goal is delta Ij, which will be the Cij and the boundary condition will be Cij 0, which we already know, okay, that those indicate Aij. But so we need like a certain recursive formula to be able to define, to build like this Cijk from like the lower k value. So that's how we do it. Okay. Say we have a shortest path from node I to node j that make use of the node k. This is obviously what we call like the cost will be Cij k, right? Like assuming all the nodes in the intermediate nodes, you only have like the largest one will be k. Okay, so this one. So if k appear in this path, then think about this. Okay, should k appear more than one time? It shouldn't. Why? Because if k appear more than one time, say from I to k and then from k to k again and then from k to j. Okay, if this is the case, if you go from k to k here, this, if you say, oh, this is a shorter path, then from I to, consider, you connect directly here. I mean, where this part is the same as this part. Okay, meaning if you skip this loop, think about this. You could skip this loop, right? So if you skip this loop, and then the weight of this path increase, what does that mean? That means because from k go out from k and reach k, this is pretty much a loop. If this one is a shorter than from I to k and then directly to j, that means from k to k, this loop is, has a negative weight. This cycle has negative weight. If that's the case, remember, according to our definition, there is no shortest weight from node I to node j, right? Because we do not allow like a negative cycle. Okay, so having said that, k can only appear in the middle once. Okay, and in between I to k, there shouldn't be any node k appear again. So here the cost will be C, I, k, and then k minus 1. And from k to j, it will be C, k, j, and then k minus 1. Okay, and then the cost for the whole path will be this one cross this one. So this is assume we use k in the middle. Okay, this is assume we use k in the middle. If not, if k, if the shortest path from I to j does not involve node k, then, well, it will be C, I, j, k minus 1. Right? So, whichever is smaller would be our Cijk. Okay, so this one basically allowed us, okay, this recursive formula allowed us to construct like the terms with like a higher superscript from the terms of the lower superscript. Okay, so this recursive formula is important. Actually, this is this one. Either it will be mean of either Cij k minus 1 or Cik k minus 1 plus Ckj k minus 1. So the first part is like the shortest best does not to go from I to J, okay, with like the nodes like with intermediate nodes, small equal to k. The first possibility it does not involve k. Second possibility it involves k, and then there will be the case. So either one of these two cases, okay, then that's it. So in other words, okay, because we already know Cij0, right? Cij0 will be Aij, right? So we can construct Cij1 from Cij0, and we will be able to construct Cij2 from Cij1, and so on. So eventually we can reach Cij, okay, this way. So the sugar code for the forward washer is like this. So the inner nested loop, okay, for j from 1 to n, so for I from 1 to n, for j from 1 to n, basically we are trying to calculate this. See if Cij is greater than Cik plus Ckj, then you assign this one. Okay, so basically you are trying to construct like Cij with a larger superscript. Okay, but you don't have to write down the superscript again because regardless, you write the superscript or not. This loop will work the same way anyway. So the superscript actually will be the outer loop. The k goes from 1 to n. Okay. So this is a very clean algorithm that does the job. Okay, you only have 3 loops, and it allows you to calculate Cijn. Okay, at the end. And if you look at this inside here, if you want to discuss a little more, this will be a relaxation that we keep talking about in the shortest path discussion. Okay, and because we have a very simple nested loop, okay, 3-level nested loop, okay, and each level it runs from 1 to n. So obviously the time complexity is n cubed. So this is very simple, coding is simple, and it is efficient in practice. Okay, and the complexity is lower than this one. Okay, remember this one is after we do some optimization for the matrix multiplication, we still can only get n cubed log, right? But the forward ratio, well, it does not require any additional matrix like multiplication, optimization, where actually you cannot optimize any variable. But it already has like a lower complexity than the cube problem. Okay? So, that's a full wash. I mean, I understand like maybe this is covered in our structure, but for completeness, okay, we still have to cover it, okay, and also, okay, because now we cover dynamic program, you know, so this one actually is a kind of like dynamic program because you are constructing the Cij K, okay, with from the terms with lower superscripts. Okay, that basically, you know, this bottom-up approach is the nature of the dynamic program. Okay, so that's like you know, well, at least dynamic program, you learn this concept like in algorithm. Okay, class. Okay, so. Remember, like we tried this Floyd-Marshall algorithm on the directed graph. So, with that in mind, we can also use the similar algorithm to calculate the transitive closure of the directed graph. What is transitive closure? Transitive closure means like if you are able to reach you know, J from I, if you are able to reach J from I, you know, regardless of the cost, as long as you are able to reach, to go from one node to another, that means that, you know, we will mark the, you know, this one is true, okay? There's a path between node I to node J, okay? If there's no path exists, okay, between node I and node J, then we will call it false. So true is 1, false is 0, right? So yeah, that's, you know, so we call this Tij, means like if you are able to reach, we go from I to J, okay, then we call it 1, we call it true. If there exists a path from I to J, 0 or 1. Remember, we are dealing with directed graph. We are dealing with directed graph here. So, being able to reach from I to go from I to J doesn't mean we can go from J to back to I. Okay. So how do we calculate this transitive closure for all pairs of like all possible pairs of I and J? The idea is to use the Floyd-Marshall. But now, okay, instead of like calculating the cost, okay, we don't care about the cost. Okay, we care only, you know, if there's a path between them or not. So, you know, again, we have the superscript K here. Okay, Tij would be Tij K minus 1. Okay, if we are already able to reach, to go from I to J with an intermediate node lower than K minus 1, lower or equal to K minus 1, then this is 1, this is obviously 1. Okay? Or, okay, you can go from I to K and then from K to J. If there's a path somehow from I to K and then from K to J, then that's good enough. That's good too. So it will be 1 and 1. So this one will be, you know, will be 1, 2. So either this one is true or this one is true. Otherwise, you are not able to reach to go from I to J. Okay, with superscript K. Okay, so So here is like, I mean, the concept is exactly the same as Floyd Washer, the previous Floyd Washer showed its path, L with it. So, because the recursive formula is identical. And, well, we probably also need to talk about the goal here is to calculate the goal here is to calculate Tijn. So your Tij will be Tijn. Okay? And also the boundary condition, where to start first? It's a Tij superscript 0. Okay, this Tij superscript 0 is what? Is 0 if no h from I to j, 1 otherwise. So this one can be derived easily from adjacency matrix as well. Okay? So with all that defined, you are able to compute the intrinsic closure of the direct graph. Again, using the exactly same time complexity, theta and q. Okay? So now we finish two different algorithms to calculate all pairs show this path problem. Okay. One is to use like matrix multiplication, but with a little bit twist, and we are also able to actually that's pretty much a to the power n, and that a to the power n, if we want to optimize it, okay, we can do the optimization on the top of the matrix multiplication. The time complex is n cubed log n. The second one is Floyd Washer. Okay, the complex is n cubed. Okay, and there's a third one. And this third one, I think I'm sure this probably will not be covered by the data structure. Okay. So we know that we can calculate like a single source shortest path by using either Dijkstra or Bellman-Ford, right? And we know like a Bellman-Ford, if you compute like Bellman-Ford, if you try to call Bellman, because here the all pair shortest path problem, okay, in the all pair shortest path problem, the h could have negative weight. The h could have negative weight. So the Dijkstra, although the complexity of Dijkstra algorithm is lower than the Bellman-Ford, but we couldn't use Dijkstra because, as I said, like you may have negative weight h's in your graph. Okay, so yeah, we couldn't use Dijkstra, so we only can use Bellman-Ford. That is like one of the assumptions, like that's one of the reasons like we make use of it. Pretty much Bellman-Ford like for the first algorithm, right? And we end up with like n cubed log n. Yeah. So that's not ideal. But that's not ideal. Okay. But what if we are able to what should I say, like change the way of your ages in the graph. Okay, we could do the what we call graph reweighting. What if we can do the graph reweighting to make sure all the age weights are positive? Okay, now there is no negative weights. Now after this transition, there is no negative weights. Then we could, use diagram. I mean, and obviously we need to call diagram n times, right? Because we need to calculate the shortest path from every single node as a source node. But you may argue, obviously, like changing the weight of your ages, doesn't work because, well, it does not guarantee the shortest path, okay, remain to be the same one, okay, after you change the weight, okay. But here's the interesting, okay, we have a theory here, okay. Given a function h, okay, given a function h, okay, so this function h, okay, basically give a number for every node. They assign a number to every node. Okay? So for example, the u and the v, okay, each of them, according to this function h, it has a number. Okay. Now, okay, we try to assign, okay, the weight of if there's age from node u to node v, and say that the weight of that age is w. Okay. Now we are doing the graph reweighting. Okay, we call the new weight from this age uv. Okay, we call wh. uv, okay, is original weight wuv plus hu minus hu. So you add the number of the source node minus the number of the destination. Okay, so that's how you do the reweighting. Okay, if we do that, then we say for any two vertices, all the path between them, okay, will be reweighted by the same amount. So if you have many paths from node I to node j, say you have 10 passes, then these 10 passes, after you do a reweighting, okay, the previous weight for these 10 passes obviously will be changed. But the change, the delta amount of the change will be the same for these 10 passes. If that's the case, then if the previous shortest path will remain to be the shortest path after this reweighting, right? This is very important. And why? Because the weight for a path after this reweighting, it will be sum of some ages from vi to vi plus 1, blah blah blah. And the first one obviously is source node, and the last one obviously is the destination. Okay, and then because according to our reweighting, okay, each of them will be the WBI BI plus 1 plus HBI minus HBI plus 1. Okay, according to how we do this equation. And you will find that, each term cancel out each other. Let me use a figure. That's probably easier to explain. Say we have node A, node B. Okay, let's say we have two paths. We have two paths. Say it's 1, 2, 3. Okay, just for the sake of easy understanding. Okay. So after the reweighting, okay, this path, okay, the top one will be W, H. We call it P1. We call this top one as P1. The bottom one is P2. Okay. So P1, it will be W, H, A2, 1, right? Plus WH, well, 1 to B, right? According to, how we calculate the weight for the path. And according to the original, reweighting formula, it will be W, now, okay, how we obtain WH is WA1 plus HA minus H1, right? So that's the first term. And then plus the second term, it will be, W1 B plus H1 minus HB, right? So you will find that, okay, this one cancel out each other. So these two add up to be the pathway before you reweighting. It will be, the WP1 plus HA minus HB. Right? This is for the top path, right? This is for the top path. For the bottom path, it's just, basically it's like, WHP2. It will be, WH, from A to 2 plus WH from 2 to 3 plus WH from 3 to C, right? So not from C to B. And then, the first one will be WA to 2 plus HA minus H2 plus W, the second one will be W2 to 3 plus H2 minus H3. The third one will be W3B plus H3 minus HB, right? So if you add up this one, okay, these two cancel out each other, these two cancel out each other, and these three add up to be WP2. Be careful, this is WP2, this is not WHP2, plus HA minus HB, right? So you see after the reweighting, for different path, okay, their path weight, okay, will be modified with the same amount. That amount, to be exact, will be HA minus HB. Okay, so having said that, whatever path that is shortest, previous will be the shortest at the end, right? After reweighting. Because each path, the weight change, will be identical, right? So this is important. So now you know that. So based on that, we'll discuss the next, the third, all pair shortest path. Let's take 10 minutes break. When we come back, we'll continue our discussion.